Today, Anna Keeley and Monique are going to share with us from the mind of Isaac Newton. It's going to be a good time. I think this puts us officially into the 17th century or something. So maybe late 1600s, basically. Last week we were in the 1500s. The week before that we were around the time of Paul the Apostle with Heron. The week before that, a couple hundred years before that, was Archimedes, and on back we go. But remember, there was that massive gap that put us dramatically into the 1500s. Now we're into the 1600s. But I'll turn it over to you guys.
All right, hello everyone. I'm Anna. So I'm going to start by giving some background on the time that Newton was born into and like the time leading up to when he did his work. So I'm going to talk about some other mathematicians who preceded Newton, and their work would help lay the foundation for what Newton did. So Newton was born into a time when there was a lot of discovery happening within mathematics. And so yeah, we're going to talk about the leading mathematicians of his time. All right, so we're going to start, we start in the late 16th century with Francois Viete. So he was a mathematician during the 1590s. We talked before about his approximation of pi, but his real masterpiece was the analytic art. That's what it's called in French. So in this publication, he made major contributions to symbolic algebra, and he made a really important step of working toward using letters to represent number amounts in equations. So that was like unheard of at the time. Next, we have Napier and Briggs. So they were in the early 1600s, and the book describes that they introduced, perfected, and exploited the logarithm. So the log is valuable both in terms of its theoretical significance and its practical applications, and some of those applications include the pH balance system in chem and the Richter scale for earthquakes. Logs are also useful in simplifying more tedious multiplication, division, or extraction of roots. So their work on the log was really important. And it's interesting to note that the cooperation between Napier and Briggs was a contrast between what was to come in math. There was going to be a lot of bitter disputes between mathematicians, so their cooperation was unique compared to what was to come. Next up, we have Descartes. In 1637, he published Discours de la methode, which was significant both philosophically and scientifically. And its influence in math came from actually an appendix to the book, which was called La Géométrie. So this appendix was really important because it was the first published account of analytic geometry. It wasn't called that then, but that's what we call it now, analytic geometry. So yeah, it announced the marriage of algebra and geometry that would become indispensable in all subsequent mathematical work. So really important foundations laid there. So in the 1630s, we have the kid genius Pascal entering the scene. So he was really something. At 14, he was already attending meetings of senior French mathematicians. At 16, his mathematical writings were so impressive that Descartes refused to believe that a boy his age, had written it. He didn't believe that a 16-year-old had really written what he had written. And then when he was 18, he invented a calculating machine, seen there on the left, that is seen as a predecessor to the modern computer, which is really crazy because we're still in the 17th century and that led to our modern computer. He also made strides in the theory of probability, building off of the work of Cardano from a century earlier. So it's really interesting. After doing so many great things in math, he actually quit math because he said it wasn't God's plan for his life. So he just stopped doing math. But then when he was 35, he had a really bad toothache. And then he just started thinking about math. And then his toothache went away. So then he got back into math, but literally for barely a week. But in that time, he discovered the fundamental properties of the cycloid curve. But then I think he died shortly after that. So that was it for him in math. So interesting story of him in math. Next, in the mid-17th century, we have Pierre de Fermat. Fermat created his own analytic geometry independent of Descartes, and some even think earlier than Descartes did. He made great strides toward what we now call differential calc. The biggest mark he left was in number theory, where he worked on the properties of whole numbers. So it's interesting that often he just would not provide a valid proof. An example of this is the decomposition of the perfect square. So yeah, notice that equation there. So he wrote, but it is impossible to divide a cube into 2 cubes, or a fourth power into 2 fourth powers, or generally any power beyond the square into 2 like powers. Of this I have found a remarkable demonstration. And then he writes, the margin is too narrow to contain it. So he literally said, like, I found a proof, but there's just no room on the page for it. So he didn't include it. And it's just really interesting because this is still unresolved. So what he was saying that we can never find whole numbers a, b, and c, and an exponent n greater than or equal to 3, for which that equation holds true. So yeah, it's still unresolved. It's very disputed still. Euler proved it for n equals 3 and n equals 4, but beyond that, it's still unresolved.
Actually, it's resolved.
Oh, it's resolved.
Yeah, since the publication of this book, Andrew Wiles, a British mathematician, proved it in like 1998, and the proof's like over 200 pages long. We'll actually watch a movie called The Proof that interviews Andrew Wiles and his proof of Fermat's last theorem.
Okay.
So nobody believes that Fermat actually had a valid proof.
Don't they think that they know what his proof probably was and what the error
Yes,
is?
yes. If you go, there's a famous website called Archive on the web, where crackpot mathematicians will post proofs of things that they think are true, but while they're in review or whatever. And there's like dozens of people that think they proved Fermat's last theorem in this really elegant way, and they all make the same mistake, all of them. And everybody thinks that Fermat probably made that same mistake. It's kind of a trap that you fall into. It's not like that inexcusable, but it's not a valid proof. So yeah.
But is it true? Like
It's true.
Okay.
And it's also true that the margin was too narrow.
That is a true statement, apparently. But Andrew Wiles literally had to develop like a whole field of mathematics to actually slate the problem.
Oh.
So yeah, so we'll watch a movie about that. But
So it is resolved. Okay.
Yeah.
Wow. So yeah, that was his last theorem, and apparently it was right. Okay. And finally, I'm going to talk about Isaac Newton for a while and give you some background into his life. So his father died when he was very young, and then then Newton's mother remarried an older man, and the older man was excited to have a young wife, but not a 3-year-old son. So Newton was left with his grandmother, and it was really sad because like he lived close to his mom and stepdad, but like his mom just didn't really care about him. So yeah, his grandmother raised him. He was very reserved as a child. He would just read, keep to himself, and build things. He ended up going to Trinity College, and at the time when he went, academics were very poor, professors weren't really doing their job, and students just wanted to party. But Newton was still on the ball, and he could just be found walking around the grounds, just contemplating things deeply. That was very characteristic of him. And I think a story that gives you some insight into how Newton was so he was curious about light and vision. So to learn about this, he stuck a stick up his eyeball. So that's disgusting. I know. Yeah, but he was a very powerful mind. He just had a way of thinking on things until he understood them. He would just think about things continuously until he could really grasp it. An example of this is he read Descartes' geometry, which we talked about earlier. He just read that over and over until he understood it. And this was like without any outside help. He would just read it over and over by himself until he understood it, and eventually he did. So yeah, he was a genius in many different areas. His scientific renown came from his work in gravity, which turned out to be like very, surprisingly accurate for his time. And he also made many discoveries within math, including the binomial theorem, differential calc, integral calc, and also outside of math, something called the theory of colors, which has to do with the color wheel, and that's the color wheel that he came up with there. I think it has to do with he looked at a ray of light, and he could see that there were like 7 natural colors in it. So yeah, he just was very versatile and smart about many things. And yeah, now Monique is going to get into some math stuff.
Yeah. So what we're going to talk about mainly here is how Newton approximated pi, but we're honestly not even going to touch pi until like the very end. So bear with me. But this little graph right here, that's that's a preview. He found a way that he did two things. He found a way to expand a binomial using a single equation, and he also discovered how to find the area under a curve, which if you've ever taken calculus, it's called integrals. And then he put it all together. So what's a binomial? A binomial is like when we've all taken algebra 2, and that's a binomial, a plus b squared. And Pascal, we know that Pascal had this triangle, and so now we know, does anyone know anything about this triangle? If you've seen it, yeah. So the coefficients, they each they add, I can figure this out, hold on. If you add up the one above it, you get the next coefficient. And so people were expanding binomials using Pascal's triangle, but it was tedious, and Newton found a way to write an equation about this, and also it works for negative exponents and powers that are fractions, so like radicals. So that was his proof, or not his proof, his starting equation, and I didn't really know what this meant until I really broke it down. So instead of being scared, look at A plus B plus C plus D. This is essentially like a sequence that's happening here. There's a pattern that's happening here. So the beginning term is A, which is just P raised to the power of M over N. Let me explain. This right here, this is the binomial that we're trying to expand. And then M over N is the power, okay? And so as we progress through the sequence, you see that MB equals M over N times AQ. So you plug that back in there. And as the thing that's changing here in the sequence is, we can see that the next term will be like M minus, for example, to get from A to B, he did M minus 0 times N over N. And then the next, to get down to C, the coefficient was just M minus 1 times N over 2N. And then the next one was M minus 2N over 3N. So you can see that the number beside the minus N is increasing. It's just being multiplied by the next integer. And the denominator is also increasing, being multiplied by the next integer. So that's essentially what this whole thing says. And you're also putting it with the, when you multiply the whole thing by A, you know that in this term B, there's something being multiplied by P to the M over N. And in C, there is something being multiplied by P to the M over N. So eventually you can cancel out. You get to a point that you can cancel out P over M, P to the M over N. And we could go through how he simplified that, but that kind of sucks. So we're gonna move on. So Newton got to this final equation. And so if we want to, for example, let me point out that this is a never ending sequence. This goes on forever. So how did he use it? He expanded 1 plus x cubed. And as you can see, each coefficient, let me back up. The numerator on top, because this is a never-ending sequence, I was like, when do you stop? When do you know when to stop doing this? And it was when the numerator on the top eventually equals 0. And if you simplify all of this, you get the same thing that Pascal did. The coefficients of 1 plus 3x plus 3x squared plus x cubed. So that's how he did it. This also works for negative powers, and the fraction ones. This is important. What he did here. I almost skipped over it because I was like, this kind of just looks like background noise, but this is like pretty important for how he approximated pi. When you expand the binomial and it's not a whole number, it's not a positive integer, that never-ending sequence, like it never cancels out to 0, and you literally just have to keep doing it forever and ever. Yeah, he confirmed that this was like true, and that was pretty cool. Thanks, Newton. But using this, he found a way to approximate any root. What's happening here? This is just him plugging in this formula, and then he got the coefficients for a binomial to the 1/2. And what he did to approximate the root of 7 is he knows like 7. Well, another way to write 7 is 9 times 7, or like 9 over 9 times 7, which still equals 1, which can also be turned into 9 times 7 over 9. And now, if we want to take the square root of this still equals 7. Nothing has changed, but we can now do root 9 times, oh, just kidding. This has changed.
No, I think you're okay.
Yeah.
And you go equals 3 times the square root of 7 nines, right?
It should be.
Let's say right.
Oh,
7 nines is
because
1 minus
I didn't
2
factor
nines.
out. Yeah. If you factored out the 9 here, you would eventually get to 3 times the square root of 1 minus 2 over 9. This is the same thing as writing 7, the root of 7. And you get a number. You plug in this, and the decimal just keeps going forever. You can just stop when you're exhausted. Yes.
I have a question.
Yes.
Why do you think, I mean, it's clear that if he wants to use the square root of 1 minus x thing, then he needs to write a square root in that form, right? But why do you think he would want to take an x that, like, what? I mean, why 2 nines, for instance?
2 nines? Well, that would be he knows, he got this. He knows what the formula to find, like, a binomial, like 1 minus x. And I just think that 2 over 9 would be his x, or his q.
That's right. So, but so that star formula is a series, right?
Yes.
It like goes on forever. It turns out you can only plug in certain numbers into that.
Yeah.
And no, you can't just plug like 1,000 in there and hope to get something equal. So he needed that x to actually be a fraction between -1 and 1 in order for this to work.
Wow.
Otherwise, so he needed to get a number that was smaller than 1. Does that make sense?
Yeah.
For to plug in for x.
Yeah.
So that was probably mainly what he was going for.
Mm-hmm.
So,
Now we're halfway there. We know how to approximate radicals, and I found some cool art. Okay. The next part of him finding pi was integration. He called it fluxions. Is that how you say it? Fluxions. And then again, he gave us like a scary formula to find it. But if you've ever taken calculus, the way I broke it down, like what integrals are, as like you find it kind of like you're doing the opposite of a derivative. So does anybody know the power rule? Can anyone give me the power rule? Yeah.
nx to the n minus 1.
Okay.
Yeah.
Oh, yeah. So if anyone hasn't, I got no sleep. If you don't know if you've never taken calculus, what a derivative is this is like an equation that we can use to find the slope of a curve. But we're not trying to find the slope. We're trying to find the area underneath the curve. So I'll just, we know using that formula, we bring down the power, because this is like x to the n minus 1. We would bring that down so the n become a 2, and then you would you would subtract the power minus 1. So that's how you would get 2x. With the integral, you kind of do the opposite. Instead of multiplying by the, we're doing the integral of x squared. Instead of multiplying, instead of subtracting 1 from the power, we add 1. So this is, the 2 becomes a 3, and instead of multiplying just the power into it, you multiply by the reciprocal. And that's like a basic like tip of the iceberg of integrals. And that's what, not all of it, but that's what I kind of understood from here. Okay, so now we're ready to use integrals. He took a semicircle and he wanted it, the book didn't specify why, but the book was just amazed at like the numbers that Newton picked. He picked a semicircle starting at, the center was at 1/2. So this distance here is 1/2. And he knew what this equation was. He knew what the equation of this line was, and that is right there. So using that, he was able, using his binomial expansion, he figured out the exact, or an approximation of what this shaded region was. So he using what the binomial expansion, he learned the actual number, what's inside of here. But this doesn't really have anything to do with pi. And the next way that he wanted to find a different way to find this shaded region. So he used geometry. So we'll just keep this number in the back of our minds. I'm sorry. I don't know what's happening. Okay.
Probably turn the pin off. The button needs to be.
Oh, I got it. Okay. So he first did, like, he found out what the area of just this triangle was with B. It's important to note that this is 1/4, like B right here, this is 1/2 of this distance. So it just cut it in half. And he found the area of this triangle using the Pythagorean theorem. So, like, 1/4 squared, using this is the Pythagorean theorem, essentially. And he found the area of the triangle to be √3/32. Okay, so now we know this is √3/32. That's the area. And next, he found the area of sector D, ACD. So next he found like that whole piece. And what the book was like oh, it's crazy that like Newton picked all these numbers because it worked out so well. If you see like, if this was a whole circle, you would see that this would just be like a sixth. This is like, if this was a pizza, you would see that this is just 1/6 of a pizza, right? So if you got rid of, if you divided this whole thing by 2, you would see that this sector is 1/3 of the whole semicircle. And so he knew what the area of a semicircle was, and he just multiplied it by 1/3, and that's where pi finally came in. What? Now it's blue and it's not showing any. Can you see what I'm drawing? Okay, I'm sorry. I got it.
Touch the pen right there.
And he knew that this was a third because this triangle right here was a 60 30 90 triangle. So that's easy to find. So he learned that the area of the sector was pi over 4, and he knew that the triangle inside of that was √3 over 32. So what do you do to find the shaded region? You subtract those two numbers.
Hang on. Is it pi over 4 or pi over 24?
You're right, 24. Yeah, that's definitely gonna pop up in the rest. Thank you. So to get the area of that shaded region, which was like that weird wedge shaped, you do the area of the sector minus the area of that triangle. And because like normally people in his day wouldn't know how to like get this down to an actual number because there's a radical, there's pi, might as well just keep it like that. But he already figured out what the shaded region was using his binomial expansion. So when he solved for pi, he got 3.145926888. And that is how he approximated pi. And
So he would have had to do a approximation of the square root of 3 as well, right?
Yes, he did.
And he didn't have a calculator.
No.
Right? So all of that division would have been by hand and entirely.
Yeah. And then later he like went back, and like 16 years later, I don't know. He went back later and made this like way more approximate. Like he could get more numbers. So thanks, Newton, for that. Yeah. QED. Oh, does someone have a question?
I was just wondering, would he also use the binomial expansion to approximate square root of 3?
Yes. Good question. My teacher in high school said that you only have to go like maybe 4 digits in, and then who cares about the rest. But I think Newton just wanted to flex. So
Okay, so just more about Newton. In 1668, Newton completed his master's degree and was elected a fellow of Trinity College. Through the help of Isaac Barrow, Newton got a job as a Lucian professor and gave lectures on mathematical topics. Newton's reputation began to grow when people started reading his unpublished treatises like De Analysis and Methodus. Isaac Newton's first big public invention came in 1671 when he displayed his newly invented reflecting telescope at a meeting of the Royal Society in London. This device combined Newton's theories of light and his practical ability at tinkering. Today, these are still used. They have a mirror at the base rather than a heavy unstable lens and are preferred instruments of optical astronomers. So after that, Newton submitted a paper on optics to the Royal Society, but this time his ideas were met with skepticism. Because of all the negative comments, Newton decided to go into his own private world and wouldn't publish or communicate any ideas with peers. After he died, historians found unpublished scientific papers from decades in his desk drawers. Because Newton never submitted his ideas, he never got credit for some of them. In 1684, Edmund Halley finally got Newton to publish some of his discoveries. In 1687, Philosopher Naturalis Principia Mathematica came out, which is a system of the universe, a precise mathematical derivation of the motions of the moon and planets that explain the clockwork precision of all creations, ticking to the orderly rhythms of Newton's wonderful equations. In 1695, Newton left Trinity College after being there for 35 years. In 1696, Newton accepted the position of Warden of the Mint. In 1704, he published his Optics, a massive tome that did his optical theories what the Principia had done for his law of gravity. Unmatched scientist, preeminent mathematician, public servant, and Royal Society President Isaac Newton received the ultimate tribute of a king knighthood from Queen Anne in 1705. He then got the title Sir Isaac, and in 1727, he passed away at the age of 84. There is a statue of Newton to this day that is in London as well. And that's all about Newton. That's it.
Let's go into mention. I was looking in here. There's a couple of quotes in here that are kind of interesting. One of them is, well, I guess it's after for a second in case somebody asks questions, but one of them was, I was trying to find this quote where he talked about his eye. Oh yeah, here's what he did to his eye. Listen to this. This is fun. As Newton described it, he took a small stick or bodkin and pushed it, quote, betwixt my eye and ye bone, as near to ye backside of my eye as I could, and pressing my eye with ye end of it, there appeared several white, dark, and colored circles, which circles were plainest when I continued to rub my eye with a point of ye bodkin. He actually, I mean, there's a folklore tale that says that Newton also invented like a helmet that would, he suspected, especially with his bodkin popsicle stick experiments, that something was happening in the mind that would flip the image. Does that make sense? And we kind of know that that's true, that the image is actually reversed in the mind, but the mind kind of does the work of kind of flipping it back. And so what he did is this is attributed to him, created some kind of helmet that actually flipped everything upside down. And then one day he kind of wore this helmet around and was just stumbled around for a while. And then one day he woke up and everything was the right way again. And he still had the flipping upside down helmet on. So his mind had kind of done something. And then he took the helmet off and everything was flipped around again. So he had to stumble around for a couple days and then the mind would kind of flip it around. So that's one little folklore tale. I don't know if that's true or not, but it definitely somebody did it, but a lot of people think it was Newton. Another story is that he stared at the sun for like a really long time, and he kept really detailed logs about how long he would be blind after staring at the sun and things like that. So he literally abused his body for science. And finally, here's the thing that they were talking about with his approximations. In Methodus, Newton presented the value of pi to 16 decimal places of accuracy based on a 20-term binomial expansion. The one that we just looked at, it was like 6 or 7 terms or something. We did a 20-term expansion, which would have required a massive amount of by-hand computation, okay? And at one point, commenting on this approximation, he somewhat sheepishly confessed, quote, I am ashamed to tell you to how many places of figures I carried these computations, having no other business at the time, end quote. Okay, so he's an amazing guy for sure. Any questions? Yeah, there was a lot of political upheaval in those days, and basically contributing to the state was probably valued more than contributions to science and mathematics. But yeah,
Coins were being like shaved down basically, and so coins were way smaller than they should have been, and so he figured out a way to like
make sure that
that wasn't happening.
Yeah.
So he was knighted for that.
Any questions? Any questions? One thing I might have you do is actually engage, even with a computer, trying to even do part of what Newton did in this approximation. He did it all by hand, mind you, okay? All of this was done by hand, long division, nightmare, and he did it all. And one thing I will sometimes have students do is actually do a baby version of it, just to kind of see the sort of pain he put himself through. Yes. No, I mean it was fairly easy to check the work. I mean, all of the computation would have been right there on a page, anyways. But yeah. Yeah. And approximations to pi were fairly important, just because they didn't know what pi was. You know what I'm saying? I mean, they knew it was a number, but they didn't know what it was specifically. So in a lot of computations involved pi, right? I mean, because pi just shows up and, you know, it showed up in the formula for the area of a circle, shows up in the formula for the circumference of a circle. It shows up in other places as well. So they needed a good numerical approximation for this thing, because everything they did was an approximation, yes? It was all by hand computation. Now we have the luxury of computers, and computers can carry out these binomials as far as we want. We can get as high a degree of accuracy as we want. But that was not true back then. You had to just be willing to gut it out. And Newton was, for sure. Other questions? One thing I want you to take away from this is, have you noticed that these mathematicians that we have been studying, weren't just mathematicians? They did everything. Mathematics was just a component of what they did. This is sort of a part of the classical mindset, that you're not really a complete person intellectually if you just silo yourself off in one area. It's very good to kind of stretch yourself. And this is a lesson I've kind of had to learn. I probably learned it too late in life. So I'd really encourage you, you know, I mean, when you take your general education classes, I know that sometimes you tend to think, oh man, I have to sit through this literature class, right? I don't see why this is practical. Look, there's a lot of things that don't seem practical at the time that end up shaping the way that you think about a variety of things. So it's hard to, it's hard to predict just how something that you're learning might affect you later on. I mean, I read Jane Eyre in middle school, and at the time it was just like torture. I hated that stinking book. I read the whole thing, and I had to write a stupid book report. And here I am, you know, whatever, 30 years later, and I remember I remember the entire book. I remember specific characters, specific instances in the book itself. I've had tons of conversations about Jane Eyre. And actually, I sort of like it now. I've just thought about it for like 3 decades. And now it's like, oh yeah, that was kind of a neat book. Why in the world did I hate it so much when I was 12? Well, it's because I was 12, right? You have to, your generation especially, there's like this push from the academy, it's not your fault, that everything has to be obviously useful, and that you have to be able to see immediately why it's useful. And that is just absolutely stupid, okay? Because tons of stuff that was clearly useless like 300 years ago is now like super useful. And back then, everybody was saying the same exact thing. They were all saying, that is stupid. Why would you do that? Looking at complex numbers, what are you thinking, you idiots? you know? Or what is all this number theory stuff that you're doing? Nobody's ever going to use that. And now it's like the bedrock of cryptography. You know what I mean? Humans are horrible at predicting what's going to be useful. We're not omniscient. We cannot know what's going to be useful. And in the end, you need to think of it as a thought shaping exercise. It helps you think, kind of shapes the way that you kind of approach any number of things. So that's one reason I would like to go through this book. It really helps you understand. These guys took everything seriously, whether it's reading Jane Eyre or the Word of God, or doing mathematics, or thinking about physics, or mechanics, or economics, or whatever it is. They sort of looked at it all. And so I'm hopeful that, I hope that that's something you'll come away with for sure. Okay? Other questions? Other questions? All right, well, tonight, hopefully you'll get that Flatland thing done. And on Monday, I want to talk about that a little bit, okay? The first part of Flatland. It's a great book, I think. And it's an easy read. You could even go like, I mean, if you're, oh man, you go to Chuck's and over lunch, I'm telling you, you can blow through. I mean, it's a good read, I think. Okay, so enjoy. And we'll talk a little bit about that on Monday. All right?
Is there going to be like any sort of study guide for the test, or do you just have to?
We'll talk about that next week. We'll talk about the test stuff next week. Yeah. Thank you, guys.